So the second half of 4.3 will be about the graphs of logarithmic functions. And anytime you do anything involving graphing, you have to keep a few things in mind. And that first thing that we need to keep in mind is this list that we've written down 5-6 times in the past, but it's worth repeating again. Function transformations. I'm quite serious. Anytime it comes to graphs of functions, knowing function transformations will save you a lot of time and headache. So we've written it before. I'm going to write it again. It is that important. For any given function, if you add something to it, it'll always move the graph up. If you subtract from it, it'll move the graph down. If you're adding directly to the x, it'll move the graph to the left. If you're subtracting directly from the x, it'll move the graph to the right. If you're multiplying the whole function by a number, it will vertically scale by whatever number you multiply by. However, if you multiply directly to the x, it'll horizontally scale by the reciprocal of what you multiply by. So if I multiply the x by 2, I actually scale it back by 1/2. If I multiply by 1/3, I've actually stretched it out by 3 horizontally. If you multiply the whole function by a negative, it is a reflection or a flip over the x-axis. And if you multiply the x directly by a negative, it's a reflection across the y-axis. So this is a vertical flip, this is a horizontal flip. So function transformations, when it comes to sketching anything, it's a pretty good thing to know. What other aspects do we need to know in order to graph logarithmic functions? Well, recall that earlier in this unit we sketched exponential functions, and exponential functions had certain properties or attributes that were interesting to look at. So we need to know the attributes of the exponential function. And what were some key ideas or characteristics of the exponential function? The exponential function always goes through the point 0, 1, at least the basic function does. It has a default horizontal asymptote at y equals 0, and the domain was always all real numbers. And of course we have the two shapes, growth and decay, right? So we had two shapes, a growth function or a decay function. But this whole unit's all about graphs of logarithmic functions. Why am I harping or spending time talking about exponential functions? Well, the last thing we need to remember in order to understand the shape of a logarithmic function is we need to remember that logarithmic functions and exponential functions are inverses of each other. Well, so what? Okay, that's great. That's a neat trivia fact. Why does that help us? And this is the last recollection that we need to have. Right? Well, back in Unit 2, we talked about inverse functions, and we should have seen that the graphs of inverse functions are always reflections of each other's over the line y equals x. And this should make sense. Algebraically, how do we find inverses? we just swap the variables, swap x and y, and solve for y. So graphically, to look at inverses, they should be, inverses of each other, about the reflection about each other across the line y equals x. And if you need convincing, I think the above recollections, yeah, we can convince ourselves. We already knew it. This last one was from Unit 2, it was a while ago. So let's take a look at a few graphs here. All right. So I just graphed the line y equals x. And what are some common inverses that we are familiar with? Well, we know that cubing something and cube rooting something are inverses of each other. So if we look at the graph y equals x cubed and y equals the cube root of x, as you guys can see, they are indeed reflections of each other about the line y equals x. What are some other common inverses that we know? Well, we know that adding 2 and minusing 2 are opposites of each other. So let's look at the lines y equals x plus 2 and x minus 2. And it's sort of boring. They are parallel, but they are technically reflections of each other about the line y equals x. What about something more interesting? We all know that multiplying and dividing are inverses of each other. So if you look at y equals 2x, 2 times x, and x divided by 2, as we can see, they are reflections about the line y equals x. So this should confirm that last recollection that, if you have inverse functions of each other graphically, they're always reflections about the line y equals x. What does that mean for us today? Well, that means, putting it all together, all of the attributes, all of the qualities of a logarithmic function should be the same attributes and qualities of an exponential function, but all the x's and y's flip-flop. So what are some of the attributes of an exponential function? It goes through this point here. So what would be the logarithmic equivalent? We'll just swap the x and y. So instead of going through the point 0, 1, we should know that all basic logarithmic functions goes through the point 1, 0. What's another physical attribute of an exponential function? It has a default horizontal asymptote at y equals 0. So if I flip all the x's and y's, instead of having a horizontal asymptote, he'll have a vertical asymptote, and instead of y equals 0, it'd be x equals 0. So it will have a default vertical asymptote at x equals 0. And it's the last property. So the domain is always all real numbers. So if I were to flip the x and y, instead of talking about domain, I know that all logarithmic functions will have a range of all real numbers. The range is always all real numbers. It is the domain that becomes funky depending on what the vertical asymptote is. So what should the default shape be? Right. It also has two shapes. Now, it doesn't make sense to talk about a growth logarithmic and a decay logarithmic, so those terms are specifically just for exponential functions, but the two shapes of a logarithmic functions is built upon the growth function and the decay function of the exponential. So the two shapes are this. So I'm going to do the exponential shape in black and the logarithmic shape in blue. So I guess I should put that in a note somewhere. Let's see here. So here's the key. This will be exponential. And this will be logarithmic. So we know that the exponential growth function looks something like this. Actually, let me go ahead and draw the reflection line. We know that the exponential function should look something like this. It's just sheer coincidence that it looks like it's an asymptote. It's not. So the logarithmic function should go through this point here and be the mirror image of this guy. So what would the mirror image of this guy be? Well, it'd be something that looks like that. Well, what if I had the decay function? Again, the decay function should look something like this. So if I wanted to do a mirror image about the line y equals x, what would the logarithmic function look like? Well, it always goes to this point here. It looks something like that. So those are the two shapes of the logarithmic function, those two blue shapes here. Now, it all depends on what the base is. Remember, you have a growth. If the base is bigger than 1, you'll have a decay. If the base is less than 1. I'll tell you this right now, when it comes to logarithmic function, we almost always talk about bases bigger than 1. So while this is good to know, the graphs, the shapes that we're going to look at are primarily going to be this shape here. So technically it has two shapes, but we're probably going to focus on one. That's it. That's all you have to know in terms of building blocks to produce graphs of logarithmic functions. Everything else is the same when we sketch exponential functions. You got to shift that special point. You got to shift the the asymptote. In this case, it's a vertical asymptote. And how do we shift those guys? Well, you just got to be able to read function transformation. So when it comes to sketching logarithmic functions, it will be more practice reading function transformations. Let's just do a couple of quick examples here. Well, suppose I ask you to sketch f of x equals log of x minus 3 plus 1. This is the common log here. First thing you want to do is just read the transformations. And hopefully we can just see that we have an up 1 and a right 3. Those are the only transformations present. So okay, once you identify all the transformations, go ahead and do your Cartesian plane. One, two, three, 4, 5, 6, 7, 8. So the two physical attributes that we're going to shift for logarithmic functions, instead of this point and this asymptote, that would be for the exponential function. For the logarithmic function, we're going to be focusing on this point here and the vertical asymptote. So those two guys will be what we are going to shift, right? So let's go ahead and shift them. So start with here. According to our transformations, we're going to go right 3, 1, 2, 3, and then up 1 here. So that should be our new, quote, special point. Oops. There you go. So 1, 2, 3, up 1, right there. You do the same thing for the vertical asymptotes. We know that logarithmic functions should have a vertical asymptote at x equals 0. So then you just perform the transformations. You're going to go right 3, 1, 2, 3, and then you're going to slide up 1. And I hope everyone can see that vertical lines, when you slide up 1, really doesn't do anything. So that stays as a vertical asymptote. All that we have to do is sketch the shape, and because the base is 10, this is base 10 here, it has a, quote, growth shape, even though it doesn't make sense to call it a growth for logarithmic. It should look like this shape here. And again, as I said, when it comes to the basic shape, when it comes to logarithms, we typically stay with bases bigger than 1 anyway. So there you go, easy peasy. I know that my logarithm should look something like that. That is the graph of that logarithmic function. Let's do something a little bit more interesting, something with reflections and flips and so on and so forth. So let's sketch f of x equals log base 4 of negative x plus 2 minus 1. First thing we want to do is label all the transformations. So we have a down 1, we have a left 2, and we have a negative here. And notice it's inside with the x, so that's a reflection over the y-axis, right? So that's going to affect our special points. That's going to affect the shape. We'll take care of all of that. But in terms of transformations, that's the only thing that's present. So let's go ahead and draw our Cartesian plane. All right, so again, by default, we are always going to look at this point here. So what transformations do we have? You always do flips or reflections before up, down, left, right. So this point right here gets reflected over the y-axis to there. Now this point here, I need to move to the left 2, 1, 2, and then down 1. So that should be the location of our new, quote, special point. Right there. Go ahead and do the same thing for the vertical asymptotes. So the vertical asymptote always starts at x equals 0. Let's go ahead and flip him across the y-axis. Well, he is the y-axis, so he doesn't move. Let's go ahead and move him to the left 2. 1, 2. Let's go ahead and move him down 1. Again, he's a vertical line, so moving down doesn't do anything. So I hope we notice a shortcut. Just like with horizontal asymptotes, it doesn't really get affected by flips or stretches or left and right movements. The only thing that affects horizontal asymptotes are vertical movements. Similarly with logs, the only thing that affects the vertical asymptotes are horizontal movements. So we have a vertical asymptote at x equals -2. So the last thing we need to do is the shape. So again, by default, the shape should look something like this. So since we flipped it over the y-axis, he's going to look something like that. So just go ahead and draw our shape down and up. That is the graph of that function. Now, I am skipping one thing that the practice instructions will have, and that's to analyze the graph. Hey, what's the asymptote? What's the domain? What's the range? The range is very easy because it's always all real numbers. It is the domain that is going to change depending on where your asymptote is, yada, yada, yada. There's actually a quick, easy way to find the domain of a logarithmic function algebraically without actually having to graph it. This is the idea. For any logarithmic function, the argument, again, the word argument simply means the stuff inside of a log, must be greater than 0. Since the argument of a log is the output of an exponential function, when we are using positive basis, it is impossible to get an answer of 0 or a negative. So when we look at a logarithmic function, that simply means what we feed inside of a logarithmic function cannot be negative and cannot be 0. So algebraically, to find the domain of logarithmic functions, you just set the inside stuff greater than 0. So for example, if I ask you to find the domain of log base, heck, I'll even do fractionals here, log base 1/2 of 3x minus 4. It doesn't matter what the base is as long as it's the normal basis that we work with, equals f of x. If it comes to logarithmic functions, the idea is the stuff inside of a log cannot be negative and it cannot be 0. So to find the domain, you just set that inside stuff to be simply greater than 0, and then you solve. So this is a linear inequality. Hopefully it should be pretty simple to solve. We get x is greater than 4/3. That's the domain of this logarithmic function. All I'm going to ask you to do, though, is put it in interval notation. So the interval notation here is going to be 4/3, comma, infinity. Fun fact, whatever does make the log equal 0, those are your vertical asymptotes. So again, I don't need to graph this guy because this graph would be pretty funky to do by hand, but just by this simple algebra, I know the domain already, and I know that the vertical asymptote is at x equals 4/3. So algebra is pretty powerful. It allows us to extract information about a graph without actually having to graph it. Since finding the domains involves solving an inequality, find the domain of, we might be expected to solve nonlinear inequalities. So let's refresh our memories on that. Say ln of 4 minus x squared. So let's say I ask you to find the domain of that guy. So, okay, we go ahead and set the inside stuff greater than 0. Oh no, this is an inequality, and I have nonlinears. So I cannot solve this straight up. I simply can't add x squared to both sides and square roots because we don't know how square roots affect inequalities. So the thing to refresh our memories is, the first thing you want to do is pretend, so this is scratch work here. You want to pretend that it is equals to 0 and then solve normally. Again, I hope this doesn't take a lot of effort for us because this is a simple quadratic, plus or minus 2. Once you have your x-intercepts, you go ahead and plot them on a sign diagram. That's basically it. To solve a nonlinear inequality, just use a sign diagram. It's going to remain open because it's strictly greater than 0. And then you're just going to plug in numbers into this function here. Maybe plug in x equals -3. Maybe plug in x equals 0. Maybe plug in x equals 3. Whatever you want to do. You plug it into the original inequality and see whether or not you get a positive or negative answer. So in this case here, we're going to get a negative in this region when you plug in a -3. You're going to get a positive number in the middle region when you plug in a 0. And then likewise, you're going to get a negative region on the right side when you plug in a positive 3. What type of solutions are we looking for here? Well, greater than 0 means positive, so your final interval, your final solution, should be whatever region has a positive result. And we can see here, it's in the middle here. So that is our overall domain. Our domain is all numbers between -2 and 2. And for added bonus, we should know what the asymptotes are. This guy actually has 2 asymptotes. His asymptotes are plus or minus 2. But on the practice, he's only going to ask you about the domain. So that's it. Sketching logarithmic functions is just flipping the attributes of an exponential function. Once you know the basic attributes of logarithmic functions, it's just using the same function transformations, up, down, left, right, flip, so on and so forth. The second thing you'll be asked to do is to find domains by hand, and all you got to do is just set the argument, the inside stuff, greater than 0, and solve. That is the latter half of 4.3.